everyone. I'm Mike Valentine from Goldman Sachs. I'm here to introduce path tracing for IPv6, show you the problems that it solves, how we solve them. And just to mention here, this is a new IETF draft. For V6, there will be an MPLS draft to follow. And that's it. And interesting note, this is my first NANOG, and I'm presenting virtually. So hi, everybody. So here we have a massive ECMP network, right? Something everybody here is familiar with. We all build them like this for lots of different reasons. Some people build them for blast radius, bandwidth. Some people want to use switch on chips to avoid chassis, so they have a lot of sprawl. Or you do what the vendor told you to do. So we're all familiar with these networks. This network could be simplistic for some people out there. You know, vendors support 32 and 64-way ECMP. You know, they're only doing it because someone asked them to. So I can imagine that this network may be simplistic for some people. But we all aware ECMP, it's a fact of life, right? And we don't know how traffic is going to go from A to M. There's 7 possible valid ECMP paths. And when you look at this, there's 7 possible paths, but remember, we're hashing on source destination IP and source port and destination port. And source ports are ephemeral for applications. So the reality is your application traffic from A to M is taking all of those paths more than likely, right? And if you ever troubleshooted with somebody before, you know, they're not going to know their source port or something like that. So you know, there's a lot of different paths here. Imagine we had corruption at router B, and in this case, we'll say there's fib corruption, right? How do we troubleshoot this? You know, some people have over-the-top probes, right? But they can't tell you where the issue is. They just say there's an issue on the network. You don't know where the issue occurred. And frankly, you know, sometimes I don't find them very helpful, the over-the-top probes. You know, I know there's an issue because I'm on the phone with you. You know, and I need to figure it out. What happens if we had this fib corruption at B and B was sending packets to E, right? So now our path is ABELGM. You know, nobody would ever expect that. You would never look to troubleshoot that, right? So we don't know where packets are going here. Introducing path tracing. So now that we know the 7 possible ECMP paths from the prior slide, we know exactly where the packets could be going in the network. So what we want to do is monitor the hardware pipeline for how these packets are treated. So by doing everything in hardware, we're seeing the normal data path of a customer or an application traffic. So there's no punting to the CPU, no offload to co-processors. The other goal we have here is ultra efficiency for MTUs. We're adding 3 bytes per hop. There's a 12-bit interface ID, an 8-bit timestamp, and a 4-bit load. As I mentioned before, this is about IPv6 with native SRv6 support. There is an MPLS design available as well that we will not be going over. And the other important thing is with anything you're introduced, it has to work with what you have deployed. So a legacy node in this would only see this as a V6 packet. It won't have to do any of these path tracing features, and you can, you know, fill in the gap. So time, right? How do we spend time from A to M? Assume we solve the first question. The path is ABGM. How are we spending that time? A thing to note here, and it's totally out of scope, is we're assuming we're keeping accurate time in our network. I think most of us today are using PTP to get accurate network time, and we're just taking for granted that you have PTP. Otherwise, you know, if the timing's off, everything's off. So what path tracing can do is look at the time and put a timestamp per router. So how is the time spent to get from router A to router M? And we're going to do that at every hop. So at router B, we'll record the time, and router G will record the time, and we'll record the time it comes in on router M. So what about the load at each hop? So we're going to monitor the interface load at each hop. So on router B, you can see the interface load is roughly 1/4. On router G, the interface load is roughly 3/4. So along with the timestamping at every hop, we're going to need interface load. So load. Before we mentioned that there's a 4-bit load ID field. And I know most of you think, what can I do with 4 bits, right? I get a measly 16 values. We implement this logarithmically. So we're going to add emphasis on the higher values, right? We're looking at things in the 80s and 90% to have smaller, you know, intervals between the buckets, whereas if your load is between 10 and 15%, we really don't care. So what we're looking at today is every X seconds, a line card CPU is going to compute the average load. He's going to translate that into the 4-bit representation. And together, he's going to write that with the outbound interface. This behavior is simple in the data plane. Everything we do here is optimized for hardware, so we're writing at a fixed offset. And that fixed offset, we're going to put the load variable in. So from a hardware perspective, this is constant. It's easy to do. And the line card CPU would update this every few seconds. In future generations of MPUs, ASICs, this can be done at microsecond speed. So here's a super high-level hop-by-hop overview of what we're going to do, right? So we have your standard IP6 header, right, on router A. Then we have this hop-by-hop pad tracing option, which we'll go over in greater detail in a few slides. We have the load at router A, the latency at router A, and next hop is router B. Router B, we have the same information. We still have the IPv6 header. We have the load at B, the latency at B, the next hop of G, et cetera, at G. So this is a super high-level overview, and in following slides, we'll get into greater detail. These are some of the design objectives, what goals we were after when we were putting this together. Number one goal, get the most out of your router, right? No to little extra processing done. Use the same forwarding plane as application traffic, your customer traffic. We don't want to be special. We don't want to punt the CPU because that's not the data plane, right? We want to experience what everybody experiences. There's various vendors involved here. We're working with all of them to make sure this is all true. So that is a key thing here. These statements, we want everything to be true. Everything should be done in hardware. And the things we're optimizing for now are MPU processing, right? Minimize the number of read writes, minimize the depth of the read writes, maximize read write at fixed positions, right? We want to know where in that packet we're writing stuff. Avoid header insert and resize. And as stated before, minimize that MTU, right? If we're clogging the network with all these frames and packets, it's not traffic your customers can use or your applications. And then we have the hop-by-hop collected data. We call this MCD, and it's highly compressed, right? I mentioned before, it's 3 bytes per hop. And then the other thing we want to do is minimize hardware complexity by leveraging SDN. So we're looking here at node M. The package traversed from A, B to G. We've collected all the data in the packet. And from node M's perspective, we want to get the most out of the router, right? He should encapsulate this in hardware and send it to your SDN app or collector, whatever you want to call it. This isn't like IPSLA. We're not looking to do any computation on the router. The router, the CPU has more important things to do than that because we'd quickly overload the CPU here. So the goal is to get everything off of the router. So when you get to the analytics engine, right, he can view this data. He has the list of collected IDs in the path. He has the timing, the history at each hop. You can highlight hotspots. And the beauty of this being in a time series database is you can highlight hotspots from an hour ago, 2 hours ago. So if you were in a more reactive position and someone called you up and said an hour ago, my application had a hiccup, you can go back in time and look, right? And say, oh, there was a hotspot an hour ago, in this particular queue. And yeah, it did impact you. Other things you can do are consistency checks, right? You have expected paths, via PC versus the actual forwarding path, right? Are they different? And once you have this information, what can you do with it? You could trigger a change of path and segment routing or MTCP, anything. Think of closed loop, automation. I tell, engineers that I work with, now that we have the data, what can we do with it, right? Because data is key. We didn't have this information in the past to this level of detail and granularity. Now that we do, what can we do with it? So having the data is key, and the sky's the limit. Once you have it, you can easily write application or closed loop automation. And the other thing here is, just to reiterate again, Router M is doing this in hardware at line rate. It's, sending to the SDN app. There is nothing software here. Now we'll get into more detail about everything. These are roles in the data model, more down to the packet level. So here we have the source. And the main thing off of this slide, the source is originating the probe. The probe is not coming from the analytics engine, right? The probe is originated in hardware at the source. And at the source, he's going to collect the data. He's going to connect the timestamp, the outbound interface, the interface load, and send it on its way. Some interesting things you can do. You can set a range of sizes for packets, DHCP values. on these things. So you can look at individual queues, right? You can do packet sizes for your probes. So here's an example of the packet generated by the source. You have your standard IPv6 header, like I mentioned before. You have the DCP value, which I believe will come in handy, flow labels, etc. Your standard source address, destination address. Then we go to the hop by hop header, and we have a new pad tracing option type here. And then we have this MCD, that midcoin compressed data stack. So the new piece is the PT option. And then we have our segment routing header, where we have our SID list, and then we have a new segment routing header, pad tracing TLV. And that's where we're going to put the timestamp, the outbound interface ID, and the outbound load. So at this source router, right, if you could see in the packet here, we have the 64-bit timestamp of the source node, we have the session ID, and we have a sequence number. Session ID, it's that probe's series of data. So that session ID will remain constant for a probe's lifetime of this one. Sequence number would be the sequence number of a packet, right? And you can imagine when you get to analytics, you can do some good things if you have sequence numbers. But note the 64-bit timestamp. We'll get back to that on some following slides. So now we have the midpoint, and that midpoint is collecting that data, that MCD. And as we mentioned earlier, it's 3 bytes per hop. You have that 12-bit interface ID, which is not globally unique. It can be repeated on each router because the analytics engine knows the router that it's collecting from, because via the MCD field, he knows which router that stamped it. Therefore, he knows the interface ID is on that router, right? We have that 4-bit interface load that we talked about before, and we have that 8-bit timestamp. And with that 8-bit timestamp, if you notice the previous slide, we have a 64-bit timestamp at the beginning. Now we can use a truncated timestamp because we know the starting time. And we can use this truncated timestamp to represent various possibilities. For example, if you had an intercontinental backbone you were looking at here, you could say, I want to use 7 bits for milliseconds and 1 bit per microsecond. Or if you're in a data center, you could do 2 bits per millisecond and 6 for microseconds. And remember, just said before, goal is hardware friendly. Shift and stamp behavior at line rate. So everything here will be done at line rate. And then we have shift and stamp at B. So this is the NCD section under the hop by hop header. And as I said before, everything is a fixed offset. So we're going to move 3 bytes to the right. We're going to stamp MCD in the first 3 bytes. So right now in MCDB, we're stamping the interface ID, the load, and the timestamp. Right now we get to G. You can see we have the MCD for router B is already in the field there. Right, we're going to shift again to the right. We free up our 3 bytes. We insert our MCD for router G. We send it on its way to the sink. Once we get to the sink, we're going to timestamp, encapsulate, and forward it, and record reception data. So, we are not doing any analytics here, hardware friendly. I use the IPL SLA example. No computation is done on this box. We just say, go to the collection engine and take it from there, right? Analytics are all done off the box. In the packet forwarded by the sink, right? We have the IP6 header. Destination is the regional collector or collector. We have the segment routing header as well, just from before, from all the packets. If you notice, this is very similar to the packet generated by the source. It'll have the 64-bit transit timestamp. So we have the starting time in 64, truncated time in the middle, and the 64-bit timestamp at the end. The session ID and sequence number are going to be zeroed out, right? That data is already in the packet, so he doesn't have to collect it. We don't want him reading further into the packet than he has to. Remember, hardware friendly, key goal, right? And then we're taking that original path tracing packet in its entirety, encapsulating it in this, and sending it to the regional collector. So all that data from before is already in this packet. So we're putting this new header on it, this new segment routing header, the path trace TLV, encoding this data at the sink, encapsulating the old packet, and sending it out. Just a note here, we're not looking at the outgoing interface and load, it's the incoming interface we're looking at on the sink. Right? Outgoing interface is going to be the interface to the collector, and we don't really care about that, right? And then you get to the regional collector, and what he's doing is just ingesting these probes in the time series database. And then this is an example of all the collected data, right? So at the source, we have the 12 bits for interface ID, 4 bits for interface load, the 64-bit PTP timestamp. Midpoint is the 3 bytes, right? 12 for interface, 4 for load, 8 for time truncated timestamp, and the sync is pretty much the same as the source. I showed this slide earlier, but I just want to reiterate, now that you know the things you're going to gather, you can do a lot more analytics than you thought. Because we're tracking sequence numbers and we can send packets of varying sizes and at varying speeds, frequencies, we can deduct packet loss, right? You can deduct packet loss in a queue. You can see time, one queue is congested over another queue. You can now take, actions based on those. This queue is congested, move my, SRTE path. This queue is congested, put in a ticket to add interface bandwidth, right? An automatic ticket to add more ECMP links, which is, kind of why we're here. The sky's the limit. Whatever you can think of, you can do. And now we look at pad tracing versus alternatives, what's out there, right? Because I know everybody is like, oh, we've done this, why reinvent the wheel? And, I think in the previous slides, we kind of explained what the benefits are. But here, if you want to compare, pad tracing is a much smaller overhead, than INT, IFA, and IOM, right? They're 20, 32, and 20 bytes respectively. Header processing is much simpler. The alternatives adjust the header size at every hop. The offsets are at different locations, right? So this is not as hardware friendly, whereas in pad tracing, it's hardware optimized. Everything is in a fixed position. Header offset's always the same, right? Reiterate, right? Hardware line rate. Because we know these things are in fixed positions, et cetera, we can do this in hardware, today. We've been working with Cisco, Broadcom, Marvell, others to do this in hardware at line rate. Other options, they're not widely deployed, possibly because they're not, done at line rate. The other thing we're doing, right, we're looking at the true path of a packet in hardware. We want to experience what our applications or our customers are experiencing. We don't want to be punted to a CPU or anything or OAM assist. We want the true data path. We want the real value. And the other is a smoother deployment, right? If a hop in the middle doesn't understand this, it's a V6 packet. So that's the beauty. Insertion is quite easy in a network. So where are we today? What's the ecosystem? What's going on? How's standardization going? Ecosystem. So there's a broad ecosystem here, right? We've mentioned Broadcom, Cisco, Marvell, others. Broadcom has the Jericho 2 implementation today. It's actually in shipping microcode. So you could call up your favorite vendor and say, please implement this. Or if you write your own software, you could do it yourself. Cisco has this in the Silicon One and the ASR 9K Lightspeed ASICs, and Marvell in their Presto line. There is strong interest from operators. This is currently being looked at in labs by several large operators. They're keen to get this moving, and the open source community is out there. There's P4, so there is actually P4 implementation of this. So you can do this if you use P4. There's a P4 implementation today. There's Linux, FDIO, Wireshark. Wireshark could see these packets and tell you what it is today. TCP dump, etc. So there's broad industry support for this. People are behind it, and standardization. So this was submitted to the IETF in March 22. This is the IPv6 version, and by the time you see this, I believe the MPLS draft should be actually submitted as well. So that's where standardization is. So in conclusion, with pad tracing, right? So now we have the capability to deterministically detect ECMP pads, right? We're implementing this at line rate in the hardware-based pipeline and ultra MTU efficiencies, that 3 bytes at every hop. So if you take away 2 things from this, it's that this is hardware friendly, done at line rate, and it's ultra efficient in terms of MTU, right? We don't want to fill our links with our traffic. We want our customer or our application traffic to be on those links. So the ecosystem, as mentioned before, it's rich, right? We have Broadcom, Cisco, Marvell, and others. Since the beginning, we've always wanted this done in hardware at line rate. The hardware vendors have been involved since the beginning. Strong operator interest, right? I mentioned this prior. People are using this, testing it out now. The open source is there, the code is written, it's out, and is currently being standardized by the IETF. Thank you very much, and if you have any questions, please let me know.
If anyone locally has any questions, you can step up to the microphone or use the chat. We do have a couple questions remotely. See, Matthew Pitak asks, how does your time series database keep track of changes in interface IDs when cards are inserted or removed in devices along the path? Or are interface IDs generated at startup for every possible interface that can be put into every device at any point in its life?
So there's two questions there. Say the first one again. So if a new interface, if a new line card was put in, right? So this is more like a configuration thing, a template you could have, but you could use the same value as before, right? That was in there if you swap like for like. If you add a new line card with more ports or something, right? You would have to adjust the values in the node. That's an implementation thing, or like your, how the interfaces are numbered, et cetera. They don't have to be sequential. They can be anything, but you would, if a session was using an ID for an interface and you used ID 1 and you put in something and changed it to 2, right? That particular session would essentially be restarted. You couldn't, on the fly, that's not going to change, right? So if a line card gets put in or anything like that, a new session ID would have to start. But that's an implementation specific thing. I suspect, some vendors may have a crafty way around that. I'm not a vendor.
Any other questions locally? We do have a comment remotely from Steve Rodrigue. He just comments that this is another type of packet to block at the edge of the network. We don't want to be flooded by fake path tracing packets.
Okay. Is that a question or a comment?
Don't think we have any other questions remotely right now. So any questions locally? All right, I'd like to thank you again for presenting.
Okay, thank you. Thanks, everybody.